Hello students, welcome to this lecture number 19 on sequences and series. We will be learning De Morgan's and Bertrand test and Gauss test for the convergence of a series of positive terms. We will be learning about these two tests. So here we go. First of all, before we start the other two tests, we must know what is Cauchy's condensation test. Cauchy condensation test says that if An is a decreasing sequence, all right, if An is a decreasing sequence of non-negative terms, all right, then this series and this series converge and diverge together. Converge and diverge together. So this is Cauchy's condensation test, that this series and this series converge and diverge together provided An is a decreasing sequence and uh, decreasing sequence of non-negative terms. So using Cauchy's condensation test, we can prove that this series summation 1 over n log n raised to the power p, as n varies from 1 to infinity, is convergent if and only if P is greater than 1. We are given that P is positive. Alright, P is positive. So this series is convergent if and only if P is greater than 1 and divergent for P less than 1. So we have to show this result, that this series is convergent if and only if P is greater than 1. So how do we show? Using Cauchy condensation test. So Cauchy condensation test says that this series and this series converge and diverge together if An is a decreasing sequence of non-negative terms. Now this, if P is positive, then this is uh, An equal to 1 over n log n raised to the power p. This is a decreasing sequence of terms if p is positive. Alright, so if p is positive, first of all, let's take an to be 1 over n log n raised to the power p. First of all, consider the case when p is less than or equal to 0. If p is less than or equal to 0, then 1 over n log n raised to the power p would be greater than or equal to 1 over n. Alright, p is negative. For all n greater than or equal to 2, this would be greater than or equal to 1 over n, and summation a 1 over n is divergent. This is uh, easy to see by Cauchy's general convergence of theorem. We have already done that summation 1 over n is divergent. So by comparison test, this series is also divergent. So we have shown that for p less than or equal to 0, this series is divergent. Now if p is positive, then n log n raised to power p is an increasing sequence, right? If p is positive, then n log n raised to power p is a increasing sequence, and right, and an is a decreasing sequence. So an is equal to 1 over n log n raised to the power p. So that would be a decreasing sequence. So by Cauchy condensation test, this series and the series 2 raised to power n a to n would converge and diverge together. Now what would be 2n a to n? This would be equal to 2n into 1 over 2 raised to power n log of 2 raised to the power n raised to the power p. This would be this 2n and 2n cancel. So summation, this is simply 1 over 2 raised to power p you can take out. So it is this is log of 2 raised to power n can be written as n log 2 raised to the power p. So log 2p comes out. So it is simply 1 over n raised to power p. And 1 over n raised to power p, we know that it is convergent for p greater than 1 and divergent if p is less than or equal to 1. So uh, hence this series also is convergent for p greater than 1 and divergent for p less than or equal to 1. So that means summation an is convergent if p is greater than 1 and divergent for p less than or equal to 1 by Cauchy condensation test. So we have proved that this series is convergent for p greater than 1 and divergent for p less than or equal to 1 using Cauchy condensation test. Uh, we have another result that would be using we will using in the for coming up theorems, and that result is this, that if an and bn are two positive term series such that an over an plus 1 is greater than or equal to bn over bn plus 1, an and bn are both positive term series, and if this happens for all n greater than or equal to m, then we have the following results. Number one, the convergence of Bn implies the convergence of An, and the convergence of An, and the divergence of An implies the divergence of Bn. The convergence of this series Bn implies the convergence of the series An, and divergence of the series An implies the divergence of the series Bn, provided this happens and An and Bn are positive terms positive term series. All right, so we will be using this result in the coming up De Morgan's and Bertrand test. So this is De Morgan's and Bertrand's test. De Morgan and Bertrand test says that if an is a series of positive terms, and if the limit of an over an plus 1 minus 1 into n minus 1 into log n, if this limit as n tends to infinity is equal to L, then this series is convergent if L is greater than 1, and this series is divergent if L is less than 1. Alright, this is De Morgan and Bertrand test. If this limit is L, then we have convergence for L greater than 1 and divergence for L less than 1. So how do we prove this? We compare the series An with the series Bn. And what is the series Bn? Okay, compare the series An with the series Bn, where what is Bn? Where Bn is equal to 1 over n log n raised to the power p. Okay, uh, n varies from 2 to infinity. So we have just seen that by Cauchy condensation test, this series is convergent if and only if p is greater than 1. This series is convergent if and only p is greater than 1. So we compare the series An with the series Bn, where Bn is this series, and this series is convergent if p is greater than 1 and divergent if p is less than or equal to 1. Now you find Bn over Bn plus 1, Bn over Bn plus 1 is equal to this, and it can be written in this form. All right, and log of n into 1 plus 1 plus 1 over n can be written as log n into log of 1 plus 1 over n, all right, divided by log n. So this is equal to 1 plus 1 over log n into log of 1 plus 1 over n raised to power p. All right, so you expand log of 1 plus n by using this formula. Log of 1 plus x is equal to x minus x square by 2 plus x cube by 3 minus x4 by 4 and so on. So using log of 1 plus n can be expanded like this. We have raised to the power p here. All right, and then using the binomial expansion, 1 plus x raised to the power p is equal to 1 plus px. Using that formula, you can write it as 1 plus p into log n into this plus other terms, uh, and square terms, etc. So this is if you multiply this bracket with this, you get 1 plus 1 over n and p over log n into this plus uh, p over log n into 1 over n into this plus other terms. Alright, so this is equal to 1 plus 1 over n, p over log n, p over uh, n log n we have taken common, and what remains is 1 minus 1 over 2n plus 1 over n plus 1 over n 3n square, 1 over 2n square. So it is 1 plus 1 over n, p over n log n, 1 plus 2, 1 plus 2n plus minus 6n square, etc. Alright, so we have reached here. What we are calculating, we are calculating bn over vn plus 1. So now we discuss these cases. Case 1 is if L is greater than 1, this is L and this is 1. If L is greater than 1, then you can choose P. Alright, if L is greater than 1, choose P such that L is greater than or equal to P and P is greater than 1. Alright, so if L is greater than 1, choose P such that L is greater than or equal to P and P is greater than 1. And summation Bn we know is convergent for P greater than 1. Alright, summation Bn, this is summation Bn. Summation Bn we know is convergent for uh, if P is greater than 1. So summation Bn is convergent if P is greater than 1. Alright, so uh, summation Bn is convergent if there is natural number n for all n greater than or equal to n. Summation Bn is convergent. So by comparison test, summation An would also be convergent. So you have to write An here. Okay, summation Bn is convergent because P is greater than 1. So summation An will become convergent if there exists a natural number m for all n greater than or equal to n such that An over n plus 1 is greater than or equal to Bn over Bn plus 1. This we discussed uh, here. Here. Alright, an over an plus 1 is greater than or equal to bn plus bn implies that bn convergent would imply an is also convergent. So bn is convergent for p greater than 1. So an will also be convergent if this happens, and bn over bn plus 1 we have already calculated is this. So an over an plus 1 is, you bring this 1 to the left hand side, minus 1 is greater than or equal to 1 over n multiplied by n both side, and then again subtract by this 1, and then you multiply it by log n both side and you get this. So if you take the limit of this as n tends to infinity, you get only p. So this limit we are calling as L. So L must be greater than or equal to p, and that is true. L is greater than or equal to p. So so an would be an is convergent if L is greater than 1. We have proved if L is greater than 1, then an is summation an is convergent. And now we will prove that if L is less than 1, if L is less than 1, this is 1 and this is L. If L is less than 1, you can choose a number P such between 1 and L, so that L is less than or equal to P and P is less than 1. Alright, if L is less than 1, choose P such that this happens. Alright, and for p less than 1, summation bn is divergent because summation bn is summation bn is which series? Summation bn is this series is summation bn, and this series is divergent if p is less than 1. Right, so if p is less than 1, then summation bn is divergent. So by comparison test, the summation an will also be divergent if there exists a natural number m such that for all n greater than or equal to n, an over n plus 1 is less than or equal to bn over bn plus 1, and bn over bn plus 1 is this. And alright, and then you bring this 1 to the left hand side and multiplied by n, and again bring this one to the left hand side and multiply by log n, and what remains, and then you take the limit as n tends to infinity, what remains is p. So and this limit we are calling as L. So L must be less than or equal to p, which is true. L is less than or equal to p, so summation an is divergent if L is less than 1. So if L is less than 1, summation an is divergent, and the De Morgan Bertrand test fails if L is equal to 1. So we have proved De Morgan Bertrand test. Alright, if summation an alright, if this was De Morgan Bertrand test, if this is a series of positive terms such that this limit is equal to L, then the series is convergent for L greater than 1 and divergent for L less than 1. That we have proved. How did we prove? What we used to prove this? We used this, number one, this theorem to prove this, that if an over an plus 1 is greater than or equal to bn over bn plus 1, then convergence of bn implies convergence of an, and divergence of an implies divergence of bn. This is what one theorem that we used, and another result that we used is that this series summation 1 over n log n raised to power p is always convergent for p greater than 1. Okay, this series is convergent for p greater than 1 and divergent for p less than or equal to 1. This result also we used to prove De Morgan and Bertrand test. I hope this is clear to you. Next test we have is Gauss test. Gauss test says that if an is a series of positive terms such that an over an plus 1, right? If an is a series of positive terms such that an over an plus 1 is equal to 1 plus lambda over n plus an over n raised to power 1 plus lambda. If you can write an over an plus 1 in this form, if you can write an over an plus 1 in this form, 1 plus lambda over n plus an over n raised to power 1 plus delta, where delta is positive. So you have the power of n is slightly more than 1. Okay, and then you have some other terms, nth terms. This is alpha n, so not an, this is alpha n, and the power of n is 1 plus something, this is delta. All right, and then you have 1 plus lambda over n. Then the convergence of an is decided by this lambda. All right, then and also the sequence an should be bounded. Also the sequence an should be bounded. Then the series an is convergent if this lambda is greater than 1 and divergent if this lambda is less than 1. So the coefficient of 1 over n decides the convergence or divergence of the series. The series is convergent for lambda greater than 1 and divergence for. So to check the convergence of the series, you just have to write an over an plus 1 in this form, where, and then you have to check the coefficient of 1 over n, and if it is lambda, then lambda will decide the convergence. So how do we prove this result? So this is convergent for lambda greater than 1 and divergent for lambda less than or equal to 1. So it is given to us that an over an plus 1 is equal to 1 plus lambda over n plus alpha over n raised to power 1 plus delta. So you bring this one to the left hand side, an over n plus 1 minus 1 is equal to lambda n over this, and then you multiply it by n both side and take the limit as n tends to infinity. So limit of this as n tends to infinity, because this is n raised to power delta and delta is positive. So this will go to 0, and this limit would come out to be lambda. The limit would come out to be lambda as n tends to infinity. So this limit is lambda. Um, alpha n is bounded and 1 over n delta approaches to 0 as delta is positive. So by Rabi's test, if this limit is equal to lambda, then by Rabi's test an would be convergent if lambda is greater than 1 and divergent if lambda is less than 1. Okay, this is using Rabi's test. So convergence for lambda greater than 1 and divergence for less than 1 using Rabi's test. So if lambda is equal to 1, then Rabi's test fails, and if lambda is equal to 1, then n into an over an plus 1 minus 1, this would be equal to 1 plus, okay, if lambda is equal to 1, this would be 1 plus an over n raised to power alpha over n raised to power delta. Alright, so you again bring this one to the left hand side, alright, and then multiplied by log n both side. So you have alpha n log n divided by n raised to power delta. Alright, this is this, and if you take its limit as n tends to infinity, so it is limit of this as n tends to infinity. So limit of this as n tends to infinity, alright, it would be 0, alright, by L'Hospital rule, by L'Hospital rule, alright. And the limit of this as n tends to infinity would be 0 because the derivative of alright, because alpha n is bounded, this is bounded, and log limit of log n over n raised per delta as n tends to infinity is 0 because delta is positive. Alright, you can apply L'Hospital rule to find this limit. This limit would come out to be 0, and 0 is less than 1. So this limit is less than 1, and this limit means less than 1 means by using De Morgan's and Bertrand test. Alright, if this limit is less than 1, if this limit is L and L is less than 1, then the series diverges. Alright, so for lambda is equal to 1 also the series diverges, and for lambda less than 1 also the series is diverges. So the series converges only when lambda is greater than 1. So this series is convergent if lambda is greater than 1 and divergent for lambda less than or equal to 1. The remark here is that this test never fails, because if lambda is equal to 1, then also we have the result that the series is divergent. If lambda is less than 1, then also we have the result that the series is divergent, and series is convergent only when lambda is greater than 1. So this test never fails, and the Gauss test is generally applied when ratio test fails, and it is possible to expand an over an plus 1 in this form in powers of 1 over n. Expand an over n plus 1 in powers of 1 over n, and using binomial theorem. So Gauss test is very important, and we will do an exercise based on Gauss test. First of all, we will do one exercise based on De Morgan Bertrand test. For example, test the convergence of this series. Test the convergence of this series. First of all, you write the nth term. Nth term is this. Then you write a n plus 1th term. Replace n by n plus 1. This is a n plus 1th term. And then find a n over a n plus 1. A n over a n plus 1 comes out with this. And then take the limit as n tends to infinity. And the limit as n tends to infinity would be 1 over x. So by ratio test, the series would be convergent if 1 over x is greater than 1. That means x is less than 1. And the series would be divergent if 1 over x is less than 1, that means x is greater than 1. So the series, by ratio test, the series is convergent for x less than 1 and divergent for x greater than 1, and the ratio test fails if x is equal to 1. If x is equal to 1, the ratio test will fail, and if x is equal to 1, an over an plus 1 is simply 2n square, 2n plus 4 square divided by 2n plus 3 square. If x is equal to 1, then an over an plus 1 is simply this, and if you expand it the squares etc., you get this, and then you subtract minus 1 from this, we get this, and ultimately you can write it in this form. And if you uh, find the limit of this as n tends to infinity, if you find the limit of this as n tends to infinity, this limit would be 4 over 4, which is 1. Alright, so Rabi's test, in the case of Rabi's test also, you have got limit L is equal to 1. So Rabi test is also failing. Okay, first our ratio test was failing for x is equal to 1. Then for x is equal to 1, we found out this limit, and this limit comes out to 1. So Rabi's test has also failed. So we have reached here n over n into an over n plus 1 minus 1 is equal to this. So you subtract minus 1 once again, and we get this. Alright, and then you multiply it by log n, then you multiply it by log n, and we have got this expression, and then you take the limit as n tends to infinity. So if you take the limit of this as n tends to infinity, so that is the limit of this as n tends to infinity, which would come out to be now limit of log n over n as n tends to, this limit would be minus 5 over 4, and limit of log n over n as n tends to infinity would be 0. Alright, by L'Hospital rule. uh, sorry, after this we have this. So this is minus 5 by 4, and this limit would be 0 using L'Hospital rule. This limit would be 0, so you limit is 0 and this is less than 1. So we have got that this limit is less than 1. So by De Morgan Bertrand test, if L is less than 1, then the series is divergent. So this series is divergent in the case when x is equal to 1, and the series is also divergent when x is greater than 1. So series is divergent if x is greater than or equal to 1, and the series is convergent if x is less than 1. So that completes the proof of this, and let's now do an example of Gauss test also. So discuss the convergence of this series 1 plus alpha beta over 1 gamma x, alpha into L plus alpha plus 1, beta into beta plus 1, 1, 2, 3, 1 into 2, gamma into gamma plus 1, x square, then alpha alpha plus 1, alpha plus 2, beta beta plus 1, beta plus 2, 1, 2, 3, gamma gamma plus 1, gamma plus 2, x cube plus so on. So you have to discuss the convergence of this series. So you find the nth term would be alpha alpha plus 1 up to alpha plus n minus 1, beta beta plus 1, beta n minus 1, and 1 2 3 up to n, and gamma gamma plus 1, gamma n minus 1 into x raised to power n. This would be nth term. Then you also find the n plus 1th term, replacing n by n plus 1, replacing n by n plus 1, you get n plus 1th term. So if you divide nth term by n plus 1th term, you get this n plus 1 into gamma plus n. All right, or everything would cancel out. An would be n plus 1 into gamma plus n. All right, and alpha plus n into beta plus n, and 1 over x. This would be an over an plus 1, and this, if you multiply and divide the numerator and denominator by n square, you will get this expression. All right, and if you take the limit as n tends to infinity, so all these limits would become 0. All right, so what remains is just 1 over x, and by ratio test this series would be convergent if this rate, if L is greater than 1, that means if x is less than 1, and this, it would be divergent, the series would be divergent if 1 over x is less than 1, that means x is greater than 1. So series is convergent for x less than 1 and divergent for x greater than 1. If this if x is equal to 1, if x is equal to 1, then limit of an over an plus 1 would be 1. So that means the ratio test will fail. So ratio test fails. Uh, Now an over an plus 1, if x is equal to 1, then an over an plus 1 would be simply this 1 plus 1 over n, 1 plus gamma over n, 1 plus alpha over n, 1 plus beta over n. This can be written as 1 plus 1 over n. Alright, an over an plus 1 can be written as 1 plus 1 over n into 1 plus gamma over n into 1 plus alpha over n raised to the power minus 1 and into 1 plus beta over n raised to the power minus 1. All right, this is an over an plus 1, and now you expand these using binomial theorem. Expand these, so this is 1 minus alpha over n plus alpha square over n square, and this expansion would be 1 minus beta over n plus beta square over n square using binomial theorem. And then if you multiply the first two terms, you get this, and if you multiply these two terms, you write first few terms, the terms containing 1 over n and the terms containing 1 over n square, etc. All right, and if you multiply these two brackets, then you write the constant term 1 into 1 is 1, and then write the terms which will contain 1 over n. The terms which will contain 1 over n would be 1 plus gamma minus alpha minus beta, and all the other terms will have 1 over n square as common. All other terms will have n 1 over n square common. So we know that the coefficient of 1 over n decides in an over an plus 1. Okay, this is the value of an over an plus 1. So by Gauss test, in the expansion of an over an plus 1, the coefficient of 1 over n decides the convergence or divergence of the series. So this series is convergent if the coefficient of 1 over n is greater than 1, that means this, if gamma is greater than alpha plus beta, and divergent if the coefficient of 1 over n is less than or equal to 1. Less than or equal to 1. Okay, Gauss test does not fail. For less than or equal to 1, the series, that means if gamma is less than or equal to alpha beta, then the series is divergent, otherwise the series is convergent. So the given series is convergent if x is less than 1, right, and divergent if x is greater than or equal to 1. So we have completely discussed the convergence and divergence of this series using the Gauss test. So that is all. So what we have done, let's just revise quickly. What we have done in this lecture is, first of all, we discussed the Cauchy condensation test. Alright, first of all, we have discussed the Cauchy condensation test. Cauchy condensation test that says that if an is a decreasing sequence of non-negative terms, then this series and this series converge and diverge together. Using Cauchy condensation test, we proved that the summation of 1 over n log n raised to the power p as n varies from 1 to infinity. This series is convergent for p greater than 1 and divergent for p less than or equal to 1. Okay, this series p is positive always. So this, we discuss the convergence of this series using Cauchy condensation test. The proof of this is here. Alright, using that we discussed that this series is convergent for p greater than 1 and divergent for p less than or equal to 1. Then we discussed form, one form of a comparison test, that if you have two series an and bn, and if an over an plus 1 is greater than or equal to bn over bn plus 1 for all n greater than or equal to m, where m is any natural number, then the convergence of bn would imply the convergence of an, and the divergence of an would imply the divergence of bn. All right, so this test is comparison test, we have already proved in the previous lectures. So using all this information, we started proving De Morgan Bertrand test. De Morgan Bertrand test says that if you have this series, then you find this limit an over an plus 1 minus 1, then again subtract minus 1 multiplied by n, and then again multiplied by log n, and then find the limit as n tends to infinity. All right, so if this limit, find an over an plus 1 minus subtract 1, then multiplied by n, and then again subtract 1, and then multiplied by log n, and then find the limit as n tends to infinity. If this limit is l, then the series is convergent for l greater than 1 and divergent for l less than 1. This is De Morgan Bertrand test, and we proved this by comparing the series an with the series bn, and this is series bn, and this series we know is convergent for p greater than 1 and divergent for p less than or equal to 1. Alright, so we compare the series an with the series bn, and then we find bn over bn plus 1 to be this, and we have already discussed its proof. We don't have time to go into that. And then we discuss the Gauss test. Gauss test says that if an is a series of positive terms, and an over an plus 1 can be written in this form: 1 plus 1 over n into lambda, and then some terms containing higher powers of n, then the coefficient of 1 over n lambda decides the convergence. The series would be convergent if lambda is greater than 1 and divergent if lambda is less than 1. So the proof of this was pretty easy, using ratio test and Rabi's test and De Morgan test. We could prove that this series is convergent if lambda is greater than 1 and divergent if lambda is less than or even equal to 1. So Gauss test never fails, and Gauss test is applied when an over an plus 1 can be expanded in powers of 1 over n. And then using we have done one exercise using De Morgan Bertrand test and one exercise using Gauss test. All right, so that is all in this lecture, and we will continue. That also completes your section 3 of series. We will be starting section 4 from the next lecture, from alternating series. So that is the end of section 3 in series. We will continue doing uh, further the results of the series in the coming up lectures. Thank you.